This is what it looks like for a machine to learn an algorithm. This is one neuron in a transformer. Here's the exact same data shown in 2D. So this video is trying to describe a transformer. In order to follow along, I would recommend knowing how a transformer works and to have read this paper. This progress measures paper by Neel, Nanda et al. When I read it, I was blown away. It's totally changed my understanding of what neural networks could do, optimization, what could be done with vectors and vector spaces. And so I set out to understand how this model had implemented the modular addition algorithm at the deepest level that I could. So this video is my attempt to describe that learned implementation. Okay, so I created this function. This function, I believe, represents the essential components in the learned solution. So everything here, I believe, is the core of the algorithm, and stuff that was in the model but not required for the algorithm to run, I did not include. So this is just the algorithm and described in as few lines of code as I could. So it takes an A and a B, a set of frequencies that you can choose for the model to use, vocabulary size, number of neurons, D-model, dimension, width of the model, and then optionally you can pass in magnitudes and phases for the unembed matrix, as well as there's some norms that normalize the sinusoids in the output of the model to kind of keep it comparable with Neel Nanda's original model. So really quickly, what this function does is it takes some frequencies, makes waves out of frequencies and phases. It does that for a fundamental frequency and a harmonic. It combines them into a 1D wave. From there, two 1D waves are created. They're the same exact wave, one for A, one for B. They are set on the last two axes, so they each get their own axis. Then they're added with a bias. Then the weights are created with this function here. And this is like the core of the algorithm. These represent the W out weights. And the network learns this function through training. After that, the output is created with this matrix multiplication with the waves that are ReLU'd here and the weights. Then the unembed matrix is created using the magnitudes and phases given or random ones. They're normalized, and then from there the logits and answers are calculated, and given the A and B passed in, C is pulled out and returned. You may be wondering, where's the attention mechanism? And I believe it's not core to the algorithm necessarily, but it can be replaced with this plus sign, and the algorithm will just run fine. And another thing that I will justify later is the fact that the waves are not in a superposition in this function, as they are in the embeddings in the real model, and a lot of other activations in the network. But a linear transformation is able to pull frequencies out of superposition. And I will describe that and the requirements needed for that and try to provide some rationale as to why they're not there. But they would just make things a lot more cluttered in this function needlessly, because I think the core of the algorithm is in the MLP. Okay, so now I want to talk about how this algorithm is implemented. In the learned network model, the attention transforms the embeddings into Q, K, and V vectors. So this here is a concatenation of query, key, value, patterns, their products, as well as the attention Z output, which is the result. So for A and B, you have Q, QA, QB, key A, key B, value A, value B. They're all similar. Over the A axis, it's constant over the B axis for all A's, and it's constant over the A axis for all B vectors. So these value vectors are multiplied with this pattern. Now this is no longer constant. The pattern has sinusoids in both directions, but there is an orientation to it. Like the pattern for A looks like this, B like that. So it still has a axis alignment of some kind. But so these value vectors get multiplied by these patterns to produce this product for A and B. This is like mid-matrix multiply, so this isn't seen in an activation, but these two get summed in that operation to produce this. Now this is where things change in the network. Instead of having an axis aligned or only working on one axis for A and B, they're added together. So that's the crucial thing, is that they're added together. For grins, this is just value vector A plus value vector B. It's very similar. So if you were to take out the QK transpose part of this and just add the embeddings, really, I think that would work. Okay, I want to work backwards from the end of the model to get to the MLP. Here we have the logits. This axis is the answer C. So if you increase the answer C, the logits shift. So if the answer is 20, down here we have A equals 20, B equals 0. A equals 19, B equals 1, 18 and 2, and so on. And it wraps around, so when A equals 112, B equals 21, and that continues. So this diagonal pattern forms from the solution of modular addition, just falls out of that problem. And you can see that in the final steps of the network. So all the logits have this doubly repeating, or not doubly repeating, but symmetry here. And there's no longer sinusoidal patterns along the A or B axis. It just eliminates all of that and forms these diagonals. This is the W unembed, and this is the final residual stream. So the MLP does something to switch the format of everything from 2D sinusoidal to this diagonal structure in order to give the correct solution. Okay, what we're looking at here is the final residual stream. Also, in back of this magenta stream, this is the unembed matrix. This x-axis is the B position, going from 0 to 112. And this axis here is the A axis. It can change, slide around. But currently, we'll keep it at 0. So, for instance, right here, this peak at 50, B equals 50. 0 plus 50 equals 50. Now, if you increase A by 1, the whole thing shifts to the left. Now 1 plus 49 gives you this answer, 50. And the entire structure circulates, wraps around to give every answer modularly. And these are the real weights of the activations right here on top of the real weights of the trained network from Neel Nanda's work. This type of behavior is what's required to get a low loss, because what it is the final vectors in the residual stream, they dot with the unembed matrix. So it's a measure of similarity between the unembed and the final vectors in the network. I'll show this with this kind of hacked function where I just take some random weight matrix that kind of looks in the same shape as the unembed matrix, make it into a circulant version, meaning that every row is just a shifted version of itself, and then just like calculate the loss on that. And if you do this, float64 says it's 0. So this is what the network is trying to do. The network is trying to make some structure that just basically follows along the unembed. And this is the same case for any of the residual stream dimensions. They all do the same thing. It's not perfect, but it's close enough to get pretty good loss. Okay, we'll talk about the neurons now. This is where the good stuff happens. So here are the neurons related to frequency 14. These are synthetic, these are real. So the neurons have this structure, no matter what frequency. They have this scheme where they're symmetric, and as you go through the phases, they diagonally shift, retaining symmetry like that. So those are all the neurons for frequency 14, but all other frequencies would operate the same way. But the higher the frequency, the more of a mess it is to see on the screen. This one's really nice because you can clearly see each cycle in the wave. So these are your neurons. You have this palette of phases from here to here. From that, we need to transform it with a set of weights into this, the MLP out. So we're going from a ReLU sum of 𝐄𝐏 and 𝐄𝐏 at a bunch of phases to a single 𝐄𝐴 plus B plane wave, where A meets B. And that's in order to dot with this, which is the unembed. So this is where some magic happens. For one, the wave troughs have been cut off the input by the ReLU. So we need to manufacture troughs by multiplying peaks by negative weights. So you have these phases. The way you do this is if you apply a positive weight at the beginning, so like this, these two peaks, get halfway through here like this, then apply a positive weight again, then at the end, then you have a piece down here to connect that diagonal. Because in order to connect this middle diagonal along with this one, you need the phase space to be traversed twice as fast in the weights. So that's exactly what happens. These are the weights. These are ordered by neuron phase and also output phase. These are all of the residual stream dimensions. And these are the phases pertaining to the frequency 14 components that went into the output dimensions. So they're ordered by phase on both axes. So if I scroll through the neuron phases, you can see that this, in back of this, by the way, is the cosine function from this function. So it's just a cosine of output phase minus twice the neuron phase. And you'll see that as I go through the neurons, this wave will traverse through twice as fast. So it goes through one cycle and then another full cycle. And these are the weights of the trained network in front. So they're pretty close. They're not exact because the phases of the neurons in the network are not evenly spaced. Like here, we're following to a specific grid of output phases, but the network doesn't necessarily abide by some kind of a grid. It just does whatever phases it wants and makes sure that it has some kind of a distribution. But you'll find that they clump up into groups of 3 or 4 phases. And so like you can tell like these first 3, if you watch the learned weights, they'll kind of remain in place as the function goes across. And then by the time you get to this one, it jumps and does a couple more there. It's like kind of groups of phases that it likes and kind of gravitates towards for some reason. But anyway, this is the function the network learns to produce these diagonals from a regular sinusoidal pattern like that from the neurons. A couple more things to show you about the weights. So here are the weights again through training. So this is over the output phase axis. These are showing the neuron weights this time. And these are over the output weight axis, but also the training axis will be evolved through the animation of this. So you can see it gradually forms into that cosine. And it's a little jagged, like I was saying, that it likes to pick its own phases and magnitudes. But if you, really quickly, it is kind of cheesy, but if you interpolate the phases to a line on the x-axis, it smoothens out a little bit. Towards the end, it refines itself to be pretty cosine-like. Okay, another analysis here. I took every training checkpoint for the W-out weights and went through frequency by frequency and analyzed the output and neuron phases for those frequency neurons. Then I did a correlation with the cosine function with the actual weights. So I took the output phase, neuron phase, and I performed a correlation measurement with the weights. So what you end up with is, for each frequency, they're monotonically increasing. Like it starts out with the first 5 checkpoints. Like for instance here, 26, 62, 81, 82, 85. So it's from the beginning, there are no negative correlations anywhere around here. I mean, it probably because of the random seed of the network, it just kind of found the frequencies pretty quick. But yeah, it's monotonically increasing. By the time you get to the last 5 of 500 checkpoints, it's still increasing, but just barely. But there are no, it never goes down. So if you sum all of these, is what I've done here, and I've put this on the graph with the test loss and train loss. So you can see that the correlation with cosine for function is monotonically increasing for every frequency, all the way through training too. So like it's still going up, even though there's not much happening in terms of the loss with the model from pretty early on. But if you watch the weights evolve, like the last 300 checkpoints, which like not much going on here with the losses, but this thing is actually increasing quite a bit and refining itself, so it's interesting. So I want to talk about the performance of this thing. It's kind of interesting. Like, it gets really good loss. If I run this on a few different runs with random frequencies, random magnitudes and phases, we're keeping the same frequencies. It typically gets like 1e-8. You know, it's really good loss, like 1 to 5e-8, something like that. It stays kind of within that range, but it's quirky. Like, if you were to set the phases or magnitudes differently, they impact the loss quite a bit. If the magnitudes are such that they're very uneven, like they're very way random, like sometimes like some of them are 0, sometimes some of them are way bigger than the other ones, they get normalized afterwards. But if some frequencies are very low, that is bad for the loss. It goes up. And also with the phases, if they aren't set up properly, you'll get a bad loss too. Usually if you just kind of set them up to be some kind of distribution that's somewhat random but spread across the entire phase space, then you're okay. But it gets really good loss. When you compare it to like E1-8, 1-E08. So now this third example is compared against the original network. And this is interesting. It gets a very low loss, lower than the model. But the interesting thing is I've run a lot of these random samplings from magnitudes and phases to check this out. This is about optimal. Like, so there's something about the magnitudes and phases, probably the phases in particular, that the model has found that are particularly nice. Like, it really has done some good work there. So that's the coolest thing that I think the optimizer did, that model did, is choose very nice phases to allow for constructive interference and destructive interference when needed. But that's my intuition on this. So now I want to talk about why superposition and the embeddings and attention are able to be eliminated from this function, and try to provide some justification for that. So I'm going to talk about superposition first, because it relates to pretty much all parts of the network. Anywhere where there's a linear transformation, you are going to be filtering frequencies, shaping them however you like, adjusting the phase, canceling frequencies out. So I'll show a basic example of a filter that negates waves. This is really pretty simple signal processing stuff. But if you have these two waves, like this 5 frequency, 25, and then you sum them, and then you subtract 25 from 5. So you got these two waves. These are your two waves. They are in your residual stream. Those are the only two dimensions you've got. If you have these two waves and these weights, these are the output, these are the input. So if you do this linear transformation, this is what you end up with. An isolated 5 frequency hertz, a negation of that, isolated 25 hertz, and it's negative. So also what you can do with linear transformations is take two frequencies like this, cosine and sine, take a bunch of weights here in the form of a cosine and sine. So cosine wave, sine wave, and then the weights are also cosine and sine waves. You do this linear transformation and you get this. Now, over this output dimension, the output wave can be any phase now. So you can do a lot of things with a linear transformation just by mixing waves. Now, I did some research into taking waves out of superposition, like multiple, and I wanted to find out how many dimensions were required if you wanted n waves isolated from them all. So I ran this stuff. This is a lot of code. I'm not going to show all of it, but I'll post it. But basically, random sets of frequencies, they're harmonics. Typically, the number of dimensions needed to isolate all 10 of these is around 30 to 50. So a D-model dimension of 128 will do. I thought it would be actually kind of less than this going into this, but I also gave it the restriction that it could only be uniformly spaced phases. I think if you were to relax this, you might be able to get away with isolating those with less, but I'm not positive about that. But basically, any linear transformation is able to do a lot of filtering. You're able to isolate frequencies, combine them in different ways. You can't add new ones. Once they're gone, they're gone. Then you'll need to get them some other way by a non-linear setup of some kind. But you can do a lot of filtering. And that's exactly what the MLP does. The W and weights filter down to the fundamentals pretty nicely. So now let me talk about, so basically the justification for this is that if you have a superposition of waves to start with, like this, it's got all these frequency components, you're still able to break them down to just these. So even if your embeddings had like every frequency in them at once, you could still filter them down. That's why I thought it was just kind of clutter to be in that function. So next I'm going to talk about attention. This is the product of value and pattern for just A and then B. So you can see how there's still a axis alignment for A and B. When you sum those, you get this. And that's where changes happen in the network. After summing those two things, the matrix is converted from like from vectors being over one axis to now being symmetric with this 45 degrees. You can see this easier, I think, in another one of these heads. Yeah, so you can see these are the two products, and then there's their sum. These are what the patterns themselves look like. But now, my point is this. If you have a symmetric result out of the attention, and it's the result of adding these two 1D vectors like that, the 𝐄𝐏 transpose does add a little bit of extra frequency content due to like sum and difference frequencies, but you're still in a position where directly afterward, the model does a pretty good or hard job of filtering that stuff out. I don't think they are relevant to the computation. You could make an argument that the second harmonic is produced to a degree in this process, and it is actually, but it's also there from the beginning in the embeddings. So I don't see how this is a crucial step, this nonlinearity here. But if I'm wrong, I would love to know if somebody could hit me up or leave a comment about that. So I think that might be all I was going to say. Thank you.